Hi, welcome to this video on KNN regression. Neighbors can be used for both classification and regression tasks, which makes it a very flexible algorithm, but the way it works for regression tasks is slightly different from the way it works for classification tasks. If we have a numeric label y, then what we're going to do for a numeric label is that we take a query I and then select a neighborhood of k neighbors, call that ni. And one of the ways we could proceed then is to simply average the values of y across all those neighbors. So if we call y sub j parentheses I, the jth neighbor that is associated with I, then we could make a prediction psi I that is simply equal to 1 over k times the sum of all the values of the neighbors. And here it's not important that k has to be an odd number. We can make it an even number just as easily as an odd number. But it turns out that this is only one way in which we can actually make the prediction. We can actually also generalize the formula and say, well, let's look at all of the training instances. So we have n sub 1 of those, and then just create a weighted average across those instances. The weights here are chosen in such a way that the decrease as a function of the distance between the query and the training instance. So the general formula then for the prediction is psi I equals 1 over the number of training instances times the sum over the training instances of qj, a weight associated with a particular training instance, and yj, a particular value of the training instance. Now, the weights can be chosen in a variety of ways. Generally, we use kernels for this purpose. Here is an example of one of those kernels, an inversion kernel. The inversion kernel works something like this. If I happen upon a training instance that is at a distance of 0 from the query, then I give basically that training instance a very, very large amount of weight. The further a training instance is away from the query, which could mean that it's either has that it's to the left of the query or to the right of the query, but the further it's away from the query, the less weight it receives. And at some point, training instances may be so far away that effectively their weight is vanishingly small. But what can be done with an inversion kernel can also be done with other kernels. Here I've shown a number where I've set actually the distance to an absolute value of 1, which means that we can have training instances to the left and to the right of the query up to a maximum of 1 point. And then I've depicted here 6 of these kernels: a cosine kernel, which is the one here in the top left, a Epanechnikov, which looks very similar but behaves just slightly differently, here in the middle top, the Gaussian kernel, which is basically a normal distribution, looks pretty flat here because of the constraint I put on there, a quartic, a triangular, and a tri-weight kernel. And you see that most of them look pretty smooth. The triangular has this angular kind of relationship, and this is not even the whole set of kernels that we can choose from. We can also use a rectangular kernel, which means that we don't weight at all, that basically all of the points are weighted equally, And then we can use an optimal weighting, an optimal kernel that was proposed by Samworth that says, well, we set the number of neighbors equal to k times 2 times p plus 4 divided by p plus 2 raised to the power p over p plus 4. Here, k is the number of neighbors used under a rectangular kernel, and p, of course, is then the number of features that we have in our analysis. Of course, we don't generally know ahead of time what kernel is appropriate, so as always in this world, we end up tuning that. So let's show how that all works in tidy models. We're going to use the same predictive features that I used in class. So there were 3 that we picked in class, which had to do with stability, with the rule of law, and with government effectiveness. And in class, we predicted whether a country was a democracy or not. But what we're going to do here is we're going to predict the numeric democracy index. So we start by creating the data split the way we usually do. So in this code, we actually read world22df. Then we put country to row names. We select the variables of interest, so stability, government effectiveness, rule of law, but also the democracy index for 2022. We drop all of the missing values, and then I'm going to create a 75% split. 75% of the remaining data are going to be used for training, and the remaining 25% for testing. And we do this again, not by simple random sampling, but by stratified random sampling, where we stratify based on the quartiles of the democracy index. This then produces essentially 122 training instances and 44 test instances. The original data, after omitting the missing values, had a size of 166 instances. The model I'm going to use is a nearest neighbor model again, but now you will notice that I have turned all of the parameters that are at work in this particular model into tuning parameters. In class, when we did the classification, the only thing that I turned into a tuning parameter was the number of neighbors, and we set the values for the weight function and for the power of the Minkowski distance metric. Here we're going to tune everything. Another difference that you will notice compared to the classification is that I've changed the mode now from classification to regression, because that's what we want. We want a regression task. The recipe we're going to follow is basically a standard recipe. So I've called it here demo_recipe. We're turning dem index 22 into the outcome. We predict it with the remaining features in the training set, and the training set is this demo_train. I normalize all of these predictive features. It is not strictly necessary here because they're already all on the same scale, but it's good practice. And you'll notice that I've added actually something here at the back that we've not seen before, which is the step_core with a threshold of 0.9. What that does is it would kick out the feature that is most highly correlated with the other features, assuming that that correlation exceeds in absolute value 0.9. What remains is that we define a flow. So we have the usual workflow function, and we add the model and the recipe that I just specified. We have 3 things to train here. So that brings me now to the tuning part. I'm going to do this here using a 3 times repeated tenfold cross-validation. You can play around with this, but there's quite a bit of tuning to be done here. So 5 for the repeats takes a bit longer. I got a little lazy and I set it down to 3. 5 might be better. You've seen this syntax before, so I'm not going to dwell on it too much more. What you have actually seen perhaps not before is this specific crossing command. There was an exercise at the end of the last lecture that asked you to play with that. Here we're actually playing with it. So we're creating a grid, a demo grid here, and that is going to cross quite a few things. I set the number of neighbors from 1 to 75 in steps of 1. That gets crossed by a number of different weight functions. The ones that you see here are not all the ones that I showed you before, but you see a number of them. You see the bi-weight function, the cosine function, the Epanechnikov function, the Gaussian, the inversion kernel, the optimal kernel, the rectangular kernel, and the tri-weight. I think this rectangular misses an R here, but I think it still did it. And instead of specifying Euclidean distance, what I've done here is to say, well, pick either the Euclidean distance or the city block distance. And now we're going to run this. We're going to run this with as our performance metric the R squared. Now we're back to the performance metrics that we introduced for regression tasks, because that's actually what we're doing here. And then you will notice that the plots we get are these here. So actually it does it has here basically 2 plots, one for the city block metric on the left and one for the Euclidean metric on the right. You see the number of neighbors on the horizontal axis, and then the different colored lines pick up on the different distance weighting functions. And it looks, but it's a little hard to see, that we need rather a lot of neighbors potentially, and that we might be better off with a Euclidean distance. So it's not entirely clear if that's such a big difference, and then possibly an inversion kernel gives us the best results. So what we can now do is redo the fit, selecting the best tuning parameters, and then basically run the analysis again, and then evaluate the way we usually do. And what you will notice is that actually the optimal choice of tuning parameters in the test set gives us an R squared of 0.714. Again, not bad for just 3 predictive features, but keep that in mind, because it might be that actually a regression model with those 3 predictive features would just do as well or even better. Thanks for tuning in.